All right, we had done an example last time with a gentleman named Gauss. Do you guys remember Gauss? Gauss was a really smart, roughly 6-year-old, and he had done something where he could count things up very quickly by noticing some patterns. Okay, we're going to use his same idea, and we're going to use this method called examine a similar problem or a related problem. But our problem, just like we pointed out last time when we looked at this, is that it doesn't start at 1, it doesn't end at 100, and so forth. All right, so thinking back to over here, the first thing I did is I gave our sum the name S, right? I wrote down S equals. So that's what we're going to do with this problem as well. We're just trying to mirror what we did from the last problem, and we'll change things as needed. So this is 36, 37, 38, and then I'm going to put that dot, dot, dot there, and then I'll put the last 3 digits. So I've got 145, 146, and 147. It's not the word 2 there. It should be a plus sign. All right, so what did Gauss do next? Do you remember?
He added the first number.
He added the first number and the last number together. Exactly. So that's what we're going to do this problem too. So we're going to add the 147 and the 36. And if we do that, what do we get? 183. Okay, and so just for safety's sake, we're going to check and make sure that the second one and second to last one gives us the same sum. They should, unless we've just made an error in addition or something like that. So do they? Yeah, so they're all 183s when we add them with their sort of partner. Okay. What do we do next? What did he do next?
Add the 183 by how many numbers?
Right, however many numbers he had, and we haven't established that just yet, but however many he had, he sort of added that many 183s together. So we end up with a whole bunch of 183s added together on the right. Now, if we keep the same number of numbers and we change them all into 183s, what happens to the sum?
Double the amount it should be.
It's double the amount it should be. So we write down that this is twice the sum, 2s. Again, if you would prefer, you can write that as a 1/2 on the right-hand side, so it all stays on the right. That's fine as well. I don't care. But it's because it's getting doubled. We've got double the amount we would have originally had. Now the question is, how many of these 183s do we have? Well, that goes back to the original problems that we started with, or the original numbers that we started with. How many numbers are there? How do we figure it out? We do. We can subtract. What are we going to subtract?
147 by 36.
Very close.
35.
35. Now, let me argue about why that works. Imagine that instead of starting at 36, we actually started at the number 1. So we went from 1 up to 147. How many numbers would I have? 147, right? But what do I not have? Well, I don't have the first 35. So that's what we're really subtracting. We're subtracting the 35 numbers we don't have. Does that make sense? So when we subtract off the 35, that will give us the sort of remainder that we have after we took off the first set of numbers. What is that? 112. So down here there are 112 numbers. So what do I do now that I know that there are 112 numbers? All right, so I multiply the 112, right? By the 183, exactly. All right, so what do we get when we take 112 times 183?
20,496.
And then what?
Divide by 2.
And then we divide by 2. So what does our sum end up being?
1,248.
Awesome. Now, you're going to do an example, I think it's in your homework or maybe in the group work, where instead of it actually adding the numbers sort of in order sequentially, it's going to skip things. So let's think what we would do if instead of having all of the numbers from 136 to 147, if we only had, say, even numbers. What would we have to do if we only had even numbers in a list of numbers? We'd have to half the number of numbers, right? Because the odd ones aren't there. Does that make sense? What if it skipped by 5s? We had every 5th number. What if we had 5, 10, 15, 20, 25, 30? What would we do then? We'd have to divide by 5 because we only have every 5th number. So however much it's skipping by, we're eliminating all those skipped numbers. So if it's skipping by 5s, we'd have to divide by 5. If it's skipping by 3s, we'd have to divide by 3. Now, that doesn't change the fact that this would still be a 2s over here. You're still doubling the values you have. What it would change is it would change the number of numbers you have, right? Because you're skipping by 3s or 5s or 2s or something like that. So that's a possibility as well. So when you get to it, you'll vaguely remember what I just said, and then you can listen to the video and go like, what the heck was that again? That's how you're sort of processing that a little bit differently. All right, let's take a look at another one. This is a really great example for the category examine a simpler case. Very practical kind of thing. The Y probably has to do this every single time it figures out a league. So if a soccer league has 10 teams, each team plays every other team one time, how many games are there? How do you know? You're really close. You're really close.
I just thought of real quick, 10 teams can each play each other once. It's 10 times 10 is 100. Divide by 2 doesn't play each other.
You've missed one detail. Any idea?
Play them.
Huh?
Times 9.
It should be times 9.
Yeah.
That's exactly right. They don't play themselves. Yeah. Okay, so let's do a simpler case. Some of you are just going, you just lost me. It's okay. We're going to do a simpler case. We're going to say that we have fewer teams than we currently do. Okay? So let's just say we have 2 teams is very unexciting. Agreed? Okay, let's do 3 teams. And just for the case of argument, we're going to give them the name A, B, C. So we have 3 teams. We have A, we have B, and we have C. Now, if we were actually scheduling, we'd actually have to write down the games that would take place. So one game that's going to take place is the game where A plays B. Right? And one game is going to be the game where A plays C. And one game is going to be the game where B plays C. Now, you might be tempted to switch the orders and write the other orders as well. And if we were playing each other twice, that's exactly what we would do. We'd have BA and CA and CB. Something like a home field advantage or something like that. And there are leagues where teams play each other twice. But this is doubling the value that we actually have. Right? I mean, we don't have those extra games because we already played them. We're only supposed to play each other one time. So if we had 3 teams, they would play each of the other teams twice, right? But 3 times 2 gives me 6. That's why I originally wrote down all 6 of those so you could see where that's coming from. 3 times 2 would be 6. And then we would divide by 2 because we're removing basically what I call the double counts. We double count everything when we do that because we talk about taking A plays B and B plays A, right? If I ask Team A all the games that they play, they're going to play 3 games. And if I ask Team B all the teams they play, they're going to play 3 games. And if I ask Team C all the games they play, they're going to play 3 games. And we're going to get a lot of double counts that way. Okay, so we're trying to remove the possibility of double counts. Okay, so that's why we're dividing this by 2. So this actually ends up being a very good model for what happens when we have more teams. So now we're going to go back to the way that you had thought about it. We have 10 teams, and each of the 10 teams plays 9 games, right? Because they don't play themselves. And then that's going to both include the team, when they report back to you and say, I play 9 games, that includes Team A saying, I play Team B, and it includes Team B saying, I play Team A. So we counted that twice. So to remove the double counts, we would have to divide by 2. So instead of 50, as we were thinking maybe originally, we actually end up getting 45. So there's 45 games. So the league would actually have to figure out, right, costs for 45 umpires or whatever they've got for their, is it umpires in soccer? I should probably learn these things. I've got kids who play soccer now. Refs, thank you. Now I will know. Refs in soccer. Don't you have refs and umpires in football? Baseball? All right. Okay, I know there's one game that's weird. All right, let's try another one. Okay, I mentioned this strategy last time, and I think I told you last time too, I'm absolutely not an artist. But diagrams can be really helpful, especially when kids are very visual. So when there's an opportunity to sort of draw a picture of what you're talking about, drawing a picture is a really good plan. Now this one is an example where you might not look at it and think, hey, yeah, there's a picture. But bear with me and I'll show you. It says a store sells bicycles and tricycles. There are a total of 15 cycles in the store, but there are 35 wheels. How many of each type of cycle are in the store? Now, one thing to mention right off the bat is that you can do this with equations, okay? So that's looking at something like a high school algebra equations, because it would be a system of equations even. You'd have to have 2 equations in order to set this up with equations. And so that's fine. There's nothing wrong with that. But it's definitely overkill. We do not need a system of equations to do this problem. So I want to show you a really cool way to think about this with a diagram. So my bicycle that I'm about to draw is not going to look like a bicycle. So let's just start by recognizing that fact right away, okay? All right, so here is, oops, I thought I had my circle. Let me get it again. All right, there's my bicycle. That's probably the best bicycle I've ever drawn in this class when I've done this problem right there just for you guys, because you guys are special. So here's a bicycle, but it says that I'm actually supposed to have how many cycles total? 15. So I want this image drawn 15 times. And I am going to draw it as a bicycle because that is the fewest number of wheels any cycle has. I don't have unicycles in this problem, right? So I'm going to draw basically 15 bicycles. However you want to sort of image that, you're going to draw 15 of them. And by the miracle of technology, they all look exactly alike. 15 bicycles. How many wheels do I have if they really are all bicycles? 30. That's not enough, right? How am I supposed to have? 35. So what does that tell me I need to do? Yeah, I need to take 5 of them, and I need to add a wheel. So there's even some, these are better tricycles than they were bicycles, right? But it worked, and it worked really quick and easy, didn't it? It's pretty cool, don't you think? So, just like with all the problems, we need to make sure that we have our answer written down. So what is our answer to this problem? 5 tricycles. So 5 trikes and 10 bikes. Make sense? Great. All right, my next one is going to have a diagram with it, but it's also going to have a little bit more than just that. So this one talks about fencing in a barn. I don't know why everybody wants to fence in barns, but they do. They like to fence things in. We fence in problems in mathematics a lot. So this one's actually got a fence beside an existing barn. So we have 48 feet of fencing, so that makes sense because that's actually how you would buy fencing. You'd have to buy a roll, and it's 48 feet long or whatever. In this case, it's 48. And we're going to use one side of an existing structure. In this case, it's a barn. So that is a common way of doing a fence. Think about your fence at home if you have one on your house. You don't fence right along the side of the house, right? There's no need for that. It's already sort of a natural barrier kind of thing, okay? So we're going to actually basically create a 3-sided fence because one of the sides is the barn. And then the question wants to know what lengths would the sides need to be in order to enclose this greatest amount of area, which is important because if you're enclosing it for animals to run around, children to play in, or something like that, you would want to have a large amount of area as opposed to a tiny little, dog run, skinny amount of area, which might not be as helpful. So in terms of a picture, we're going to draw a barn. By definition, I'm telling you right now, that's my barn. And we're supposed to be drawing a fence alongside of it, right? So my fence is going to be a rectangle, something like this. Pretend that looks rectangular, it's a little bit off. What can you tell me about dimensions? I mean, this is a rectangular shape. That's reasonable if you think about the way people do fencing. And so you're not going to do a circular fence. We just don't do that. It doesn't bend very well. So what can you tell me about a rectangle that's helpful in determining these values? Opposite sides are equal, right? The top side in the picture I've drawn and the bottom side in the picture I've drawn are going to be the same value, right? So no matter what they are, and we can give them whatever name, I'm going to call them width. just because I've drawn them as though they're the shorter amount. But they're going to match, hence I gave them the exact same name, width and width. And this other side may or may not be the same value. I mean, it could be the same value as the width, that's a possibility, but it wouldn't have to, so I'll give it a different name for now and call it the length, recognizing that I might actually use the same values. Now, there is a detail that's really important. What do we know about this fence?
48 feet.
It's 48 feet. So no matter how much I'm going to do, I'm going to use all 48 feet because to use less of it would give me a smaller area. So all of these sides added together are going to be 48. Make sense? All right, so what I'm going to do next is I'm going to actually create a guess and check, okay? So in my guess and check, we're going to, let me see if I wrote this down. You could create a table if you want. Mine's going to look like a table. We're going to have a place where we guess the side lengths, and we're going to have a place where we check by finding what area we get. So I need some guesses. What would you like to make the width and or length be? Pick one, and then the other one automatically gets determined. Let's stick with whole numbers. We're only working with whole numbers in this class, actually. So until we're going to work with negatives a little bit later, but that's much later. Whole number, and we can't have negative sides anyway. So. All right, whole numbers. Somebody pick something. 16 for, would you want that to be the width or the length?
I think that would be like both, or all of them.
You want it to all be 16? Does 16 work to give me all? I think you're right. Okay, so you're going to start out with basically like looking at a square, right? It's a reasonable thing to look at. So what happens when I have 16? What do I get for my area?
256 squares.
Okay, what did you get?
250. Oh, wait, that's. Just kidding.
16 times 16?
Yeah. 256.
256. Okay, and you're exactly right. That's square feet, so I'll write in feet squared. You don't have to write it in all the way along. You could write it as the final answer. That'd be fine, too. Okay, so if I had a square, I would have 256 feet, square feet. So what could I try next?
Do width of 12 and length of 24.
Okay, so you're changing these to say 12 and 12 and 24,
Yep.
right?
Yes.
And that still all adds up to 48, right, Lauren?
Yes.
Perfect. Okay, so now when I multiply, what numbers am I multiplying? 12 times 24, right? One side is 12, the other side's actually 24. The other 12 is just the matching side. So what do I get when I do 12 times 24? 288. So hey, that's more, right? But we still really don't know if that's the most. We just know it's more. Now what?
Change one of those numbers,
Yeah,
I guess. Make one bigger.
make one of them bigger. So do you want to make? Do you think it's something maybe between the 16 and the 12, or do you think it's something still smaller than the 12? I mean, because certainly, when we went from 16 to 12, we got a bigger area. So either the 12 needs to go down to say 11 or 10, or we need to try something between the 16 and the 12. What do you want to try? You want to go down to 11, or do you want to go up to 13? 11, thank you. Somebody's going to make a decision for me. 11, 11, and what would the last piece be? 26, right?
Yep.
Okay, sorry, I thought somebody said something slightly different. Okay, so 11, 11, and 26. And then 11 times 26 would be 286. Ooh, that's slightly less, isn't it? So I'm not inclined to go down to 10. Are you? Because we went slightly down and the area actually went down. We still don't know what happens if we go slightly up. So how about we try 13 next? Okay? 13, 13, and what? 22. What does that give you?
286.
That is also 286. So what do you think? Do we have enough information to determine the largest area at this point?
Yes.
Yeah, we do. What's the largest? Well, how'd the problem word it, actually? What lengths would have to be used to enclose the largest area? So what are our lengths? We need lengths of 12 feet, 12 feet, and 24 feet, yeah. So we have to be very careful because I almost answered the wrong question, right? I almost said, and the total area is. I mean, that's a true statement. That wasn't what we were asked to find. So we have to be careful we answer the question asked. The lengths or the sides or something like that. Everybody good? All right. Another fun example of working backwards. Example 6. One winter night, the temperature fell by 15 degrees between midnight and 5. By 9 a.m., the temperature had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. And the question is, what was the temperature at midnight? So what we might want to do first is to write down all the times that they're giving us, because they gave us quite a few times. Agreed? Mm-hmm. Okay, so let's figure it out. So what's the earliest time that we know information about? I mean like the first, the one that came in first in time, midnight, I think, yeah? Yeah, I'm not inclined to think of midnight as being early. That's late, right? All right, what happens after midnight? What's the next time frame we're referencing? 5 a.m. And then what after 5 a.m.? 9 a.m. And then noon. All right, so these are my 4 time frames. And we're just going to go through and sort of make some notations about what they tell us. What happens between midnight and 5 a.m.? It drops 15. In mathematical sort of notation, what is that telling us happened? We subtracted a 15, right? So you can kind of write that to the side to remind yourself. This is minus 15. What happens between 5 a.m. and 9 a.m.? It doubles, which is, I will tell you in advance, this problem is taken straight from your book, or at least virtually so. It's terrible to talk about a temperature doubling. Because if you talk about it doubling, it's contingent upon you knowing which kind of scale you're using. Because if you double a temperature in Celsius, you will not get the same value as if you doubled it in Fahrenheit, or if you doubled it in Kelvin, which is another temperature measurement. We're just talking about the numerical value. Okay, for the sake of argument here, just pretend like we're just doing the number and stuff. This talking about. So if you double something, what does that mean? Yeah, this is a multiply by 2. And then what happens between 9 a.m. and noon? It raises 10 degrees. What does raising 10 degrees do? It adds 10 degrees. And then finally, at that point, is what they actually tell us that we know the temperature. What was the temperature at? That is 32 degrees. So we're going to work our way backwards from 32 up. So at noon, it's 32 degrees. Got to be Fahrenheit, right? I mean, in Oklahoma it would. I suppose it could be 32 negative, or 32 degrees something somewhere else. I don't know. But it'd be hot. All right, so 32 degrees at noon. So how are we going to get back and figure out what happened at 9 a.m.? We're going to do it backwards, right? So we're going to subtract. So we're going to get 22 degrees, right? Because that way between 9 a.m. and noon, it raises 10 degrees, and I'm still at 32. Then what am I going to do to get back to 5 a.m.? I'm going to half it, divide by 2 to give me 11 degrees. You got it. And then what am I going to do to get back to midnight? I'm actually going to add 15, which would bring me back up to 26 degrees. So what temperature was it at midnight? 26 degrees. And we assume it's Fahrenheit, but it didn't actually use that in the problem, so we'll just write down 22 degrees. I'm sorry, 26 degrees.
So instead of adding the 10, you just subtract?
Yes, because we're going backwards.
Okay.
When we were going down and sort of writing things right here, we were moving sort of down the list of times, and we're basically working backwards, so we're reversing it. You got it. Yes. All right, we're going to do one other kind of interesting thing. This problem refers to a question from your homework / group work that we're going to talk about. Let me kind of go through what's on this slide first, and then I'd like for you to actually take a look at your problem so that I can answer the questions that students always ask when they get to this problem. And we'll just do it all at one time. So first of all, this talks about the 12 days of Christmas. Are you guys familiar with the 12 days of Christmas, Christmas Carol? The 12 days of Christmas has religious symbolism, and this is actually what it is, so that you know, because it's kind of cool. So the 12 days of Christmas, 1, the true love refers to God. 2, turtle doves refer to the Old and the New Testament. 3 French hens refer to faith, hope, and love, the theological virtues. The 4 calling birds are the 4 Gospels. 5 golden rings are the Pentateuch, which is the first 5 books of the Old Testament. 6 geese a-laying is the 6 days of creation. 7 swans a-swimming is the 7 gifts of the Holy Spirit. 8 maids a-milking is the 8 Beatitudes. 9 ladies dancing is the 9 fruits of the Spirit. 10 lords a-leaping is the 10 commandments. 11 pipers piping is the 11 faithful apostles. And then 12 drummers drumming is the 12 points of doctrine in the Apostles' Creed. So go ahead and get out for me, if you would, your homework or your book. I'd like for you to take a look at the section where it titles it as 1-1B. So you've got section A, section B, section connections, or section C, I call it C. I'd like for you to look at section B, problem number 12. I'm totally going to swipe on your book to do it too. All right. So it says, recall the song, the 12 Days of Christmas. On the first day of Christmas, my true love gave to me a partridge in a pear tree. And they write out a few verses of this. So if you need to look up to see what the others are, you can certainly do that on your phone when you're looking at this or whatever. The first question, it says the pattern continues for 9 days. So they're actually talking about the fact that you increase one animal each day, or whatever it is, one thing each day. But you also get everything from the day before. So like if you think about the way the song's actually done, on the 5th day of Christmas, you get 5 golden rings, 4 calling birds, 3 French hens, 2 turtle doves, and a partridge in a pear tree. You don't just get the 5 golden rings. You guys familiar with that sort of concept? You get a whole bunch of gifts on day 5, whole bunch of gifts on day 12, and so forth. All right, so the first question says, which gifts did my true love give the most? So you're trying to find out which creature or person or thing you got the most of. So for instance, the partridge in a pear tree, how many of those do you get? You get 12. You get 1 every day. How many calling birds do you have? 4 calling birds. How many 4? What'd you do? You get 4 every day for how many days? 8 days from day 4 and on. So you've got to figure out how many you get each day and how many days you get them for. Does that make sense? Okay, so that's what part A is referring to. And then part B says, how many total gifts did your true love give to you? So if you've actually done part A and figured out I got this many partridges in a pear tree and this many turtle doves and this many French hens, what would you do for part B? You add them together. Does that make sense? Okay, great.